Okay, so uh, this video is going to remind us how to do the bias design for a single transistor amplifier. So what we're going to be looking at in the lab this week is a single transistor amplifier. And even though we're really not going to be looking at the amplification this week, we're going to just be looking at the bias design here. So what I'm going to draw here is the circuit that we're really going to be looking at. Now, the one I'm drawing is going to look slightly different than what you have in your lab report just because of the way that the power supply is drawn, but it's the same circuit. And so this here, I'll label these resistors. Now, for your lab, they've actually specified RC and RE. There's ways you can design without those specified, but those have been specified. So this is VCC, and then I'll put ground down here. As I said, this is designed as an amplifier here, and we don't really see it because all we're working on this week is doing what we call a bias stable circuit. So in order for us to even run this, we have to, as an amplifier, we first have to bias the transistor in the forward active region because that's where the amplification we can get from putting in a signal. And that's what we'll look at next week, is then actually amplifying with this kind of circuit. Now, before we get started with how to design this, there's some useful equations you want to remember here. For instance, that IC is equal to beta times IB. And so if we're drawing currents here, IB is going in here, and then IC is coming down, and then there's also IE here. And technically, IE is equal to beta plus 1 times IB, but we often say that this is approximately IC. And especially for design purposes, we will often use that. Then there's another thing here that we'll talk about in a second is that for design purposes, we have this R Thevenin that we have to design. And what we said is that we typically have this be 0.1 times beta plus 1 times RE is what we need the R Thevenin to be. And then we kind of go through there with some other equations, which we'll write some other equations on. But these, quite frankly, are the equations we need to get forward on our design here. Now, to remind you, the way we have here is that you can draw an equivalent circuit for this and have the equivalent circuit be something that looks like this. Where this is still RC, RE, and then this is R Thevenin, and this is V Thevenin. And to remind us, R Thevenin is simply R1 in parallel with R2, and V Thevenin is simply R2 over R1 plus R2 times VCC. Technically, it's the total voltage drop, but we're assuming that we're grounded at the bottom here. And so that's how we can get those in this equivalent circuit here, because this kind of equivalent circuit is really kind of where we start our design from. And so let's just go through an example, and I'm going to, whoops, apparently I'm forgot here that this one is not set up. It's set up for my hand to draw as opposed to it scrolling here. So let's go ahead and go through an example that's similar to what you are going to have to do in the lab. Now, this should be something that you all know how to do if you scratch off the cobwebs here. So let's do an example. Let's let, I'll go ahead and specify that RE is 1 kilo ohm, RC is equal to, come on, what's going on here? Is equal to 3 kilo ohms, and then design for bias stability and so there is nothing else here. Now I think the lab report tells you to design around a particular current. So the lab report actually gives you one more piece of information than what hey, just get a message that needs to disappear. Where's my mouse? Yes, I understand you want to meet with me. Now finally just disappeared on its own. That was annoying. So design for bias stability here. Now, typically what we want to do here is we want to design so that our Q point, which is basically our DC bias point, is in the middle of the load line. In fact, I'm going to just change the report so that it's identical to this here, meaning that instead of giving you a current, I'm going to have you design for the middle of the load line. And so to remind you, a load line here is something that always has the same shape. It's going to look something like this here. There's actually this little red bit off here doesn't actually exist there, but if I hit erase, the way I have it, it's going to erase the whole line because I have it erasing strokes as opposed to just individual pixels. But these 2 points are actually easy to determine. That's just your power supply point. VCE is of all the voltages dropping across the transistor, because this is VCE and then this is IC. Then if there's all the voltage dropping across the transistor, there can't be any current, because the current across the resistors would be 0. Well, then there's no current. And similarly here, this is assuming an unideal situation that you can never achieve, which is assuming that the transistor would be turned on and you can pump the maximum amount of a current through it. And this would be VCC divided by RC plus RE. Would be the absolute maximum current, again, you could pull there, assuming that you could have that transistor turned on with no voltage across it, which doesn't happen. So that's your load line. And then, as I said, when we want a bias in the middle of the load line, we typically want to have the bias going right here. Now, the reason for this is that this is going to actually, this point, when we start doing amplifying with a small signal, this point's going to kind of a little bit move up and down on my load line. And if I'm moving up and down on my load line, I want to make sure that I'm not hitting all the way up towards, if I was biased up in this region up at the top right here, if I was biased up there, the problem with that is the transistors, the way the current curves are, the transistor's about to shut off. And then if I was biased all the way over here, same issue. Transistor really is about to not be on anymore. And so that's why we want to put it in the middle of the load line. So what that means is our first design parameter that we set, which is usually very easy to do, is we set that VCE is going to be 1/2 our power supply. And so for our example here, I didn't specify a power supply. So let's just say I'll just go ahead and add that into my specs here, that VCC is 9 volts. And we're gonna need to know what beta is, so I'll also state that beta is 100. Okay, so I have VCE then is 1/2 VCC. So that means VCE is 4.5 volts is what I'm designing for. Now, let me scroll back up here. So I'm going to go to this equivalent circuit right here. So that means this plus minus right here is 4.5 volts. Well, that means the voltage across this resistor plus the voltage across this resistor has to equal 4.5 volts because I have a 9-volt power supply, and I'm just doing a KVL going straight down. Okay, so if I do a KVL going straight down, that's all well and good. So then that tells me here one other thing, which is important for design. And hey, you're supposed to be auto hiding for me. Why is that? Somehow that got turned off. Why is this taskbar still being here? Go away. Okay, well, I can just use there we go. That's working out for me, just using the down arrow. Okay, so sorry about that. So we have RE being 1 kilo ohm, RC being 3 kilo ohms, and VCE is 4.5 volts. But then we can just say that, well, my IC, I know that here, I'll just write it down. 4.5 volts is VRC plus VRE, which technically this is IC times RC plus IE times RE. But remember, we said an easy approximation that we do is that we basically say IC is equivalent to RE. So we say instead what we'll have here is 4.5 is equal to IC times RC plus RE. And so we really get that IC is then just going to be 4.5 volts divided by 4 kilo ohms. So if I do that here and pull my calculator up here on my cell phone, where's my calculator? There we go. 4.5 volts divided by 4 kilo ohms. And why does it have all this other crap in here? 4.5 volts divided by 4 kilo ohms gets us 1.125 milliamps. So that's what we would have for the current here. And then the next thing we're going to need here for our design is that, well, I have RC and RE. I didn't design for those, but I need to find R1 and R2. That's really what I need to find here. Now it's not letting me scroll up. Come on, scroll up. There we go. I'm really looking for this R1 and R2. Well, I'm going to use this idea of R Thevenin here and this RE here to determine what I need for my R1 and R2. And so what we're going to look at now is we're going to look at a different loop here. So we're going to look at this loop. And this loop, first off, this current going in here, this is IB. I don't know why it keeps doing this to me. It's probably because I'm left-handed. And then coming down through here, though, is IE. So I'm going to need to know both IE and IB. So this is actually, I think, an equation that's in the lab as far as for useful equations. But what we can do is we can get an equation here that says that V Thevenin oh my gosh, this is annoying me today. V Thevenin is equal to IB times R Thevenin plus beta plus 1 times RE. Now, I'm not going to go through the derivation of that. That's, again, kind of something that you should be familiar with from your previous course. And you can always just do the loop yourself. And that beta plus 1 is coming from, that IE, I forgot one other thing here, plus 0.7. And I will go back and tell you where that 0.7 is coming from. So let's go ahead and explain where that equation, I said I wasn't going to, but let's go ahead and go back and explain where it's coming from. Okay, so the IB times R Thevenin is clear. So V Thevenin is equal to this IB times R Thevenin. That's equivalent. But remember, there's this turn-on voltage here for this little base emitter junction. And that's, it's not a diode, but it's a PN junction. So we, unless otherwise specify, say that that's 0.7 volts there. So that's where that plus 0.7 came from. And then this RE, you might say, well, wait, where's the IE times RE? Well, I did that IE is equal to beta plus 1 times IB. So I just did that automatically in my head kind of thing before. And so that's where this term comes from. That's where this term comes from here. That beta plus 1 RE is I just basically substituted that in already. And so we can clearly see that in order to compute what V Thevenin is, I need to know what IB is, and I need to know what R Thevenin is. Well, IB is easy. IB is easy because we know what IC is. So IB is just 1.125 milliamps divided by 100. So if I do that, sorry, here. If I do that, I get 11, I want to make sure my units were correct, 11.25 microamps. And then R Thevenin, there is that equation that we had that this is 0.1 times beta plus 1 times RE. So that would be 101 times 1 kilo ohm times 0.1. So R Thevenin is 10.1 kilo ohms. And now we can compute what V Thevenin is. So V Thevenin is simply 11.25 microamps times 10.1 kilo ohms plus, well, this is going to be 101 times 1 kilo ohm plus 0.7. Then if we just go through and do that computation, so plus 101. We get 1.95 volts. And now we are ready to finally actually complete our design because I've got everything I need. I've got V Thevenin and R Thevenin. You're going to use these two equations here to find R1 and R2. How are we going to do that? Well, let me show you. So to do that, we're going to use the fact that R Thevenin is equal to the resistors in parallel. Come on, I don't want this. But how can I write that down? This is R2 times R1 over R2 plus R1, or R1 plus R2, doesn't matter. And V Thevenin is equal to R2 over R2 plus R1 times VCC. And so what I'm going to do here is I'm actually going to solve here for, I'm going to plug some numbers in here for this equation. And so I have 1.95 is equal to R2 over R2 plus R1 times, not 18, 9 volts. Now, there's a trick here to solving this. I'm not going to actually, try and do R1 and R2 and do all this. What I'm going to do is, it's a little trick, is that you solve for R1 or R2 plus R1. And so if I solve for R1 plus R2, you basically get that it's R2 times 9 divided by 1.95. I'm not even going to bother doing that division at this point. That's just simple, cross multiplying and dividing. But then what I'm going to do is take that, substitute it into this equation for R Thevenin. And so I know that R Thevenin is supposed to be 10.1 K. And if it's 10.1 K, well then I have 10.1 K is equal to R2 times R1 over, and then I would have R2 times 9 divided by 1.95. And so then the R2s cancel. And then you'd wind up with R1 is equal to 10.1 kiloohms times 9 divided by 1.95. And so doing that computation, we get 46 0.62 kiloohms. Something doesn't feel right here to me. We'll finish out the computation here, and then I'll see if I did something wrong here. Because I don't think I did anything wrong here. I'm just looking through here. That's definitely right. Yeah. All right. So we'll see here what we get. And then we just solve this and go back and find what R2 is. Now, the way I find R2 is I typically say that you have 1 over R Thevenin is equal to 1 over R1 plus 1 over R2, and I find R2 using that equation, another way to compute R Thevenin. And so when I do this, let's see here, what do I get here? So 12.89 kiloohms. Oh, yeah, that's right. That makes sense. I don't know where I was spacing here for a second. Yeah, no, that works. Now, of course, the reality is we don't have these kinds of resistors in the lab, so you're going to have to do some approximating. But we do have like a 47k ohm resistor, and we do have like a 12k ohm resistor. Is that going to affect where your load line position is? Absolutely. So I would do your design, but then make sure to use, before you simulate, don't simulate this as your thing, because you want to simulate at least what it is you're going to actually use to build the circuit. Okay, so that's essentially what you're going to have to do for your design portion, and that's just, again, kind of a review. The other thing is, on the lab, it said to measure IB if possible. IB is very difficult to measure, and I don't know if we will be able to measure it. The typical way you'd want to measure something like this, and I don't know if our voltmeters are sensitive enough to do this, is so we have here my little, gosh darn it, this thing is getting really annoying. I'm gonna stream soon here. Somehow it must have gotten turned off of left-handed, because it's normally supposed to, it doesn't normally do this. So measuring RC is easy if you get an accurate measure. Measuring IC is easy. You get an accurate measurement for the voltage across RC. You can do the IC is simply equal to VRC divided by RC, and you can do for the same for the IE here, and you can do VRE over RE. Now, you can do a similar thing here as far as like if you're wanting to say like, oh, well, you could say that, IB, which, I mean, this is true, but you might not have an accurate enough reading to be able to do this with this, and you might get essentially like 1 or like 10 or microamps or something. You might not get a good answer for this, or maybe you'll get 0, which would be even worse. But you can do like IE minus IC, like subtract those two currents that you've measured there. Another way to do this, but this is where I don't know if our DMMs are accurate enough to do this. Another way to do this is to put a little resistor in here. And when I say a little resistor, put like a 10 ohm resistor in there. And I mean 10 ohm resistor, because if I put a 10 ohm resistor in there, and I measure the resistance across that, not the resistance, the voltage across that will help me compute IB. But it's a small enough resistor, it's not going to affect anything in the actual circuit design. And so it's not going to affect anything in my circuit design, and so I can measure that that voltage across there, and if I knew the actual resistance of this, I could use that to compute it. But let's just see what we'd have to be able to measure if we're talking about being like the fact that this is like roughly 10 microamps going as far as my current for IB. We're talking about it having a voltage drop of 100 microvolts or 0.1 millivolts, and I don't know if our DMMs are accurate enough to measure this. However, this is a useful trick that is actually done not just in industry, but in circuit design. Sometimes you'll see in some circuit designs, and this is actually true, you'll see some things like a 0.05 ohm resistor. And you kind of be like, why on earth would you ever use a 0.05 ohm resistor? That seems stupid. And what it's usually, though, is it's usually connected up to 2 ports inside a chip. so it's usually connected up to a port inside a chip, and then the other side is connected to another port inside the chip. And what the chip is doing is it's actually measuring the voltage across that resistor to actually measure the current. And then with that 0.05 ohm resistor, when you're doing it for those, I mean, they actually are typically, they have to be like 0.1% or even better resistors that you get, because you need to know that, because the computation that's done inside the chip is assuming that it's 0.05 ohms. So you might want to try that 10 ohm trick just to see if it works. But you can also do the IE minus IC kind of deal as well. So, but do that to try and compute out what IB is. If you can't get IB, that's okay. But the reason I want you to try and do it is in your design, you assumed that beta was 150. Our design, we assumed it was 100, but for your design is going to be 150 is what you're going to be assuming. But that's not going to be what the beta actually is for the transistor. And so I'm curious if we can actually figure out what the beta is for the transistor. All right, so that will do us for that.